It's Dr. Khan here with Chapter 2's overview, Matter and Minerals. Before we can start talking about the Earth as a system and discussing things like earthquakes and volcanoes, it's important that we start with the fundamentals of what the Earth is made out of. And specifically, we're talking about the crust of the Earth, which is made up of rocks. Those rocks are made up of minerals, and in turn, those minerals are made up of the fundamental building blocks of matter, which are elements, atoms, and elements. So chapter 2 gives us a good foundation for where we're going with a lot of the geology topics that we cover in this class. When you're doing your reading for section 2.1, please make sure to pay special attention to the definition of a mineral. There are 5 parts to this definition, and a substance must meet all 5 qualifications in order to be considered a mineral. When you're reading, pay attention to those definitions, but also to the non-examples as well. So inorganic is the second item that's listed here, meaning it's not living, it didn't come from something living, and it's not made from something living. One example of something that does meet other conditions to become a mineral, but violates this inorganic part of the definition is going to be coal. So coal is made from dead plant material that's been compressed over millions of years. So we have coal, which is a living thing, or it was once a living thing, and therefore would be considered organic, and so therefore cannot be considered a mineral. Sugar, I believe, is the other example that they give in the book. Sugar is something that's produced by producers, by plants, for example, that make sugar as part of photosynthesis. So that would also not be considered a mineral, even though sugar is natural and it's a solid and it has a crystal structure and definite chemical composition. So again, as you go through these, look for examples, but also look for those non-examples as well. A rock is any naturally occurring substance that's made out of minerals or mineral-like substances. And rock is an aggregate of minerals, aggregate meaning a collection. In this case here, we have this aggregate of minerals, which is granite. That's the name of the rock. But we see that the individual components of the rock, those minerals that make up that rock, still retain their properties. Here we have the mineral quartz, the mineral hornblende, and the mineral feldspar. Section 2.2 gives you a review of atoms, those fundamental building blocks of matter. What makes atoms the fundamental pieces of matter is that they cannot be divided by chemical means. In other words, we can't do chemical reactions to further divide atoms to their subatomic particles. You'll have to know those subatomic particles, which ones are contained in the central nucleus, which is going to be your protons, have a positive charge, your neutrons, which are not charged or have a neutral charge, and then your electrons, which have very little mass. They are negatively charged particles. The book also presents 2 different models of the atom that you'll want to look at. One is kind of that classic model. We think of the electrons orbiting around the nucleus. And it turns out that's not actually how it works, although it's helpful to think about this model in some cases. We now know that electrons move around the nucleus in an electron cloud. Please take special note of atomic number. This is referring to the number of protons that are in an atom's nucleus. And this is an important number as it gives really the definition of what element an atom is. In other words, what properties that it's going to have. For example, the atomic number for carbon is 6. Any carbon will have 6 protons, and it will behave or act like carbon because it has those 6 protons. Elements are the basic building blocks of minerals. We know over 100 elements, and again, they're defined by the number of their protons. When we're talking about building minerals, we either have minerals that are made from one element or combinations of a different number of elements. So the ones that are made up of one element we call native elements. They're composed entirely of atoms of only one kind of element. So gold we find in nature. It meets the definition of a mineral. It's a solid, inorganic substance that has a definite chemical composition, crystalline structure, and it's inorganic. So sulfur as well and copper, these are good examples to stick in your head of these native elements, but there are more. If something is a mineral is made up of two or more elements, we call those chemical compounds. So here we have NaCl, sodium chloride. That's the same thing as our regular table salt. The mineral is called halite, but since it's made up of two different elements, we call that a chemical compound. Quartz is another example, a very common mineral. Silicon and two oxygens make silica dioxide. That's quartz. You should know that the periodic table of elements lays out the elements in order by increasing number of protons. So here I told you before, carbon has 6 protons. No matter which carbon atom it is, it's always going to have those 6 protons. And because of those 6 protons, it has the properties that it has. We're going to skip now actually to section 2.5. And you can go ahead and do that too in your book as well. So the testable material for chapter 2 will be 2.1, 2.2, and 2.5. 2.5 talks about rock-forming minerals. And I do need you to know that the most abundant atoms in the Earth's crust are oxygen, that's number 1, and silicon, that's number 2. The book is going to present a lot more than that. In fact, it gives you the 8 most common elements in rock-forming minerals. And it also presents that geographically as well. Again, know the number 1 and know the number 2. The mineral groups that you'll need to know include the silicates, and that's the largest or most common mineral group. Silicates are made up of combinations of 1 silicon atom, and 4 oxygens. Sometimes, though, we stick the next silicon next to it, so we get ratios like SiO2 instead of SiO4. In any case, these are arranged in what's called a tetrahedron, tetra meaning 4. So these little pyramid shapes, they're stacked together. And how those pyramids are stacked or connected to each other form our subgroups of the silicates. So pay attention to those as you read. For example, if we have independent or unconnected tetrahedra, that's an example of olivine. The pyroxene group has tetrahedra that are arranged in single chains, and then the amphibole group has a double chain tetrahedra. Based on these properties of either being independent, a single chain, or double chain, there are actually properties that we can see on the macro level, in other words, without a microscope, because of the arrangement of the atoms, which is kind of a neat thing. And my favorite example of that is the mica. Micas are tetrahedra, but they're arranged in sheets, so they're holding on tightly to each other across a sheet, across one plane, but they're not very tightly connected to each other, one sheet from the next sheet, which makes us able to actually peel off very thin layers of mica. So the feldspars are another example, but those have a 3-dimensional network of tetrahedra, and those hold on to each other a little more tightly. You should know that the most abundant group of minerals in Earth's crust are the feldspars, part of the silicates. There's a look at quartz. In terms of the non-silicate minerals, those major groups include the oxides, the sulfides, and we have the native elements as well. And there are a few more groups that are discussed a little further on as well. The oxides and the sulfides, oxygen and sulfur tend to bond with metals. And actually that's where we get a lot of our ores from, O-R-E. An ore is a rock that we would mine in order to go after a particular element or a particular substance. So for example, if we're mining for nickel or lead or iron, we don't typically find these metals by themselves in the ground. They're connected to a network of either oxygens or sulfurs, for example, and then we'll have to use chemical changes in order to free the metal from the oxygen or free the metal from the sulfur. And then again, native elements are just those elements, minerals that are made up of one element, like gold or sulfur. Here in this chart, we have examples of the oxides. Hematite and magnetite are 2 examples of ores of iron. So again, we'd get rid of the oxygens through chemical changes in order to go after the iron by itself. Sulfides, a well-known one is Galena. There's a town in western Illinois that's named after That mineral, it's lead sulfide. So by burning or smelting that mineral galena, we can get the lead by itself. Other groups to note are the carbonates. That's going to be a very important rock forming group. Carbonates give us rocks. They're the minerals that make up the rocks that include limestone and marble, and then the halides as well. Halite and gypsum are formed sedimentary rocks and are formed largely from evaporating bodies of water. So these minerals are dissolved in the water starts evaporating from an area, and this is what's left behind. That is the quick overview for Chapter 2. Again, you're going to want to take notes on Chapter 2.1, 2.2, and 2.5. And please let me know if you have any questions.